Woohoo! Welcome back. Today we're going to be doing some more trigonometric substitution. And this one is a real doozy. So I really recommend have some hydration, have some snacks, and probably plan to take a couple breaks in the middle because when I worked through this problem before, so I could get practice with it, it took 7 pages for me to write it all out. So you guys ready? We're going to do this together. Woohoo! Woohoo! Square bear is here because, again, square roots, square bear. That's what happens. So here we go. So this is a problem. I took this from your book. And it says calculate the integral. Now, this is a definite integral, so that ramps it up just a little bit. Because if we're doing any substitution, that means the limits are going to be changing. But I'm going to show you the way that I used to do it in school. And you may agree or disagree, but at least I'll show you what I'm doing. So you'll have another way to approach it. So we'll have limits. We have to deal with the limits changing if we use substitution. And then we have, pardon me, I also need to hydrate. We have a brutally complicated rational function there. And so let's take a deep breath. We can totally do this. I have 7 pages of notes that say we can totally do this, but it takes a good guide and a lot of patience. So you guys ready? Okay. You ready, Square Bear? Okay. And follow Square Bear's suggestion. If things get frustrating, maybe growl a little. That can help sometimes. Okay, so first thing to notice, because I was saying there's a square root, so the question is, where's the square root? Remember, 3 over 2 means it's to the 3rd power, but it's a square root. And we look at that and we say, well, this doesn't match that table I gave you in the last video. This doesn't look like anything we've seen before. And in fact, I believe overall it's going to take us 4 substitutions to get there. So, you guys ready? Okay. The important part to remember is, remember that I won't give you anything you can't do. Now, might it take you a lot of work? Yes. Might it be frustrating? Absolutely. But you can do it. So we're going to do it together. Let's do it. You guys ready? Okay, let me see if I can bring in a little bit more light. No, I can just bonk things around a bit more. Okay. Okay, here we go. So, at the very beginning, we need something squared inside the square root. So let's start with this very simple substitution. Because inside the square root, I've got 4x squared plus 9. So what I'm going to do is I'm going to start with u equals 2x. Then u squared equals 4x squared. That's what I'm going to put right there. And then du is 2dx. So where I see a dx, that's going to be du over 2. Now, this is a problem that the book works out in the book part. It's not from the homework. This is actually in the chapter. And the book does it really quickly. And I don't know if they're trying to show off. I don't know if they just didn't want to use the paper, but no, I don't want you to do it all in your head the way they suggested. I don't even know you can. It's possible. Perhaps some of you can, in which case, that's amazing. You guys are all amazing and very smart. But honestly, I'm going to recommend that you do everything carefully. You keep copious notes, and you number your pages so you don't get lost in the middle. Because when you have to go back to fix everything and check everything, you want to be able to retrace your steps. So, you guys ready? I've got u equals 2x. So du equals 2dx, like I have above. Oh, you can't see that. Okay. U squared is 4x squared. Also, x equals u over 2. You guys see that? Which tells me that x cubed equals u cubed over 8. Take a look at that. What do you think? Because it's u cubed on top and 2 cubed on the bottom. 2 cubed is 8. Okay. So then my integral that goes from 0 to 3 radical 3 over 2 of x cubed dx all over radical 4x squared plus 9 cubed. I'm going to convert. Now, oops, you can't see that either. There we go. So here's the original integral. So now I'm going to use all of these things to convert to u. And as soon as I make the conversion, I can do two things. I can go ahead and figure out what the new limits in u land will be. So I use the fact that u equals 2x, and then I can convert the limits. Now, when I was doing this in school, I don't know why, but that just bugged me. And so what I did, instead of converting right here, I just said, I'm just going to set up new limits, and I'll deal with it later. Because I want to focus on the integration and the limits. The limits will happen later. And I'll show you at the end how to just go bing, bang, boom to get through all the limits. If you want to convert the new limits, they're not that hard. Here, where it's 0, u is going to be 2 times 0, so this will be 0. And up here, this is 3 radical 3 over 2. U is twice x, so it's 2 times this, so it'll be 3 radical 3. So that's fine. So you can convert it at every stage. I'm going to wait till the end just because I want to show you what that looks like. Okay, so up top I've got x cubed, right? And so that is u cubed over 8. I've got a dx, and I didn't write it here, but dx is du over 2. So I've got a du over 2. And then down underneath here, I've got a 4x squared, that's u squared, plus 9 cubed. Okay? What do you guys think? So far, so good? So now I've got a bunch of numbers here, constants, and I'm going to pull them out. I'm going to pull out the 1 over 16. That is going to be the 8 and the 2. And they're going to come down here and be 1 over 16 times the integral from a to b. These are my new limits, and you can convert them or not as you choose. Then I've got u cubed all over u squared plus 9, the quantity cubed, du. What do you think? So far, so good? Okay. So I'm going to go to the next page. I'm going to copy this down. And I'm going to say this is page 2. I'm going to follow my own instructions because, again, I think we'll end up using 5, 6, 7, maybe even more pages to write this all down. Okay. So I'm going to get 1 over 16. I'm just going to rewrite what I had. Okay, that's what I had before. And I look at this and I say, okay, even though this u looks funny, now I finally see a square root of u squared plus 9. If I check my chart, which I very cleverly do not think I have right in front of me, or I would show it to you. No, I do not, sadly. Wait a minute. Ooh, do I have it? I have it. I have it. Yay. So let's check the chart. Here's the chart. And if you've got square root of something minus x squared, you use sine. If you have something plus x squared, you use tangent. Okay, so we're going to use tangent here. And so I've got u squared plus 9. Since I've got that 9 there, I want to set u equal to 3 tangent theta. And if I do that, then I have to remember my trig. The derivative is going to be 3 secant squared theta d theta. And then I also have this u cubed. This is going to be 3 cubed tangent cubed theta, which is going to be 27 tangent cubed theta. Okay, so now let me do the swap. I still have 1 over 16 out here. Again, I'm going to find new limits. So I'm just going to call these C and D. Now, if you wanted to use limits like A1 and then A2 and then A3 or something like that, that's also fine. I'm lettering new letters every time we transition. Now we're transitioning from U to theta. And again, this isn't hard to do in the moment. You just work out what the new limits are. A lot of people really like to do that. They just cut ties with the past. I am going to be focused on other things, so I've decided not to deal with it. So let's see, I get 27 tangent cubed theta all over the square root of u squared, which is this squared, so it's going to be 9 tangent squared theta plus 9, square root with a cube, and then du is going to be 3 secant squared theta d theta. Now, at this point, it would be perfectly reasonable for you to ball this up into a little ball of paper and throw it at something, because this, we've already done 2 substitutions and we don't appear to be getting any closer to being able to integrate. And this is where I'm going to ask you for faith. We are not giving you problems that cannot be done. It just means you have to crank through all the steps. Okay, so now we've gotten to this point. I'm going to pull out the 27 and the 3, and then I also want to factor out this 9, right? So 27 times 3 is 81. So let me show you the next step. 27 times 3 is 81, so I'll bring the 81 outside over 16. I'm going from C to D, I don't know what that is. Tangent cubed theta. This is going to be secant squared theta d theta. Now down here, I've got a square root of 9, and then the square root of tangent squared theta plus 1. The whole thing cubed. Now take a look at that. I factored out a 9. If I factor out a 9, it's still inside a square root. So this is going to be 3. I'm going to have tangent cubed theta, secant squared theta d theta. And then down underneath, I've got a 3 times the square root of tangent squared theta plus 1, the whole thing cubed. So far, so good? Okay. This is 3 cubed. 3 cubed is 27. So I've got 81 over 16 times 27. And now I just have the trig inside the integral. You don't have to do this, but personally, I think it just simplifies everything a little bit to get the numbers out of the way. They're just very excitable. Okay, so we've squeezed out all of the constants. 81 over 27 actually simplifies really nice. 81 is 3 times 27. So we get 3 over 16 CD tangent cubed theta all over radical tangent squared theta plus 1 cubed times secant squared theta d theta. Okay. Whoa. Okay, that's page 2. Let's go on. So let me copy that back down. I'm going to start page 3. And I have in my integral, and I'm just going to copy it. I'm not going to do anything exciting with it. When I switch pages, I never do any calculations in between. It's just too hard to follow. So I'm going to do a direct copy. Okay, that's what we had at the bottom of page 2. And so now I have to remember some trig facts to get further along. Sorry, turning off the heater under my desk because it's really cold in here, but it's also really loud and I'm having trouble focusing. So first thing I'm going to use the fact that tangent squared theta plus 1 is secant squared theta. Now, why is that useful? Well, if you've got a square root and you've got a plus or a minus, that's just miserable. There's nothing you can do with it. So let's convert this tangent squared theta plus 1 equal into secant squared. Kind of woohoo. Okay, next step. I've got the square root of something squared, so that's just the thing itself. So I've got 3/16 square root of something squared is just the thing. Okay, so now I've got 3 secants down here, 2 secants up here. Let's cancel. Secant squared over secant cubed is 1 over, see if you guys can see it, secant, right? There are 2 on top and 3 on the bottom. Okay, so then I get 3/16 integral from c to d of tangent cubed theta all over secant theta d theta. Okay, so now we can take a bit of a deep breath because this is the first time I think in this whole process that you can actually see that the problem starts to get a little bit better. What have we done? Well, we've gotten rid of all the square roots. I know, Square Bear is like, oh, so sad all the square roots are gone. But the square roots are gone. The addition and subtraction inside the square roots are gone. We've got something much simpler to deal with. And this is very, very, very exciting in my mind. Okay. Now I'm going to do some old school trigonometric manipulation. So I'm going to remind you that tangent of theta is, sine theta over cosine theta, right? So tangent cubed of theta, right? It's tangent cubed is going to be sine cubed theta over cosine cubed theta. So is this going to get complicated? It absolutely is. Okay, and then secant of theta is 1 over cosine theta. That always bugged me that that's secant and it's not 1 over sine because it should be cosine cosecant. That always bugged me, but again, dead mathematicians made these decisions. Okay, so I've got 3/16 from C to D I've got sine cubed theta over cosine cubed theta over 1 over cosine theta d theta. What do you guys think? Not too bad, not too bad. Now remember, what happens here is this, when you divide by 1 over, you actually multiply. So this is going to be 3/16. Let me see if I can get this all in here so we can save a little paper. I've got sine cubed theta all over cosine cubed theta times cosine of theta over 1. So you take this and you take the reciprocal. And then, of course, there's a d theta in there. Woohoo. Okay. That's page 3. (3/16) the integral from c to d sine cubed theta over cosine cubed theta times cosine of theta over 1 d theta. So obviously one of the cosines cancels. So I get 3/16 c to d sine cubed theta all over cosine squared theta d theta. And at this point, we get very excited because sine has an odd power. And this goes back to the manipulation we did in the previous section, where we were talking about how to integrate when you've got trig functions. And one of the keys is if you've got an extra one, so this is sine times sine times sine, you want to split it up. What does that mean? It looks like this. You want to split it up as to sine squared over sine theta over cosine squared theta d theta. Okay? And then, since sine is the odd one, right? There are 2 cosines, but 3 sines. We're going to go ahead and convert. Remember that sine squared theta plus cosine squared theta equal 1, which means sine squared theta equals 1 minus cosine squared theta. Okay? And so I'm going to plug that in there. And I really recommend that at every stage, if you're not seeing it while I'm talking about it, which I completely understand, because this is, even as long as this video is going to be, I'm trying to get through it without it being a 12-hour video. So I encourage you to pause it and to look and to say, okay, what changed? Oh, what changed with the sine squared became a 1 minus cosine squared. Okay. Okay, you guys ready? It's time for another substitution. Now, in the book just refuses to use anything but u. And I was taught that that's very, very poor manners. That if you've already used u and you're in the same problem, you use a different letter. But the book loves you. The book loves you. I love you too. But the book adores the letter U, and so I'm not going to do that. I can't. I'm sorry. I was taught that that was really, really poor manners. So I'm going to use W. Let's let W be cosine of theta. Okay? dW then is the opposite of sine theta, d theta, right? That's that right there. That's where we're going to get rid of that. And then W squared is cosine squared, right? So now we're almost there, guys. We really are. We're almost there. I've got 3/16. We need 2 new letters. I'm not going to use the letter E because that represents that number, the natural exponent, the natural base, E. So I'm going to go from f to g. Some people would not use f and g because they're used for functions, so you might want to do h and k or m and n or something else, s and t. You could use all sorts of things. So then I've got 1 minus w squared, right? 1 minus cosine squared. Sine theta d theta, that's going to be the opposite of dw. And then all over w squared. Okay. So now I want to get this minus out of there. In the book, what they do is they use it to swap this order. I don't think that's an obvious choice for a student. I understand it as a teacher, but you're welcome to do it that way. I'm just going to move the minus out of the way. So I'm just going to say this. So like that. So I take this minus sign and I bring it out. Okay, we are in the home stretch, believe it or not. So, next page. Page 5. So where we had just left our heroes, we're at -3/16 from f to g, or you can be translating and converting all the limits all the way along. And I've got 1 minus w squared all over w squared dw. Now, here's the great thing. When you've got two terms on top and only one term on the bottom, you can split them up. And then you can rewrite it like this. And this is something we can integrate without any more substitutions. We know how to integrate this. So let's go ahead and integrate it. Oh, I was so used to doing C's. I'm glad you couldn't see that whole thing. What? Pterodactyl, pterodactyl. What's the mistake? Of course, if we're doing a definite integral, there's no plus C. I just got it into my head. I've been doing so many plus C's today. Okay, it's just between us. I didn't see it. You didn't see it. Square Bear didn't see it. He ate it. Pardon me. Okay, so look at that beautiful thing. There is no integration. We're done. Unfortunately, we don't know what values to integrate on, right? So we're going to have to figure that out. But let me go ahead and let me write this out a little bit more. I've got -3/16. Right here, this is the opposite. So that's the -1, 1 over w. Do you see that? W, the -1 is 1 over w, minus w from f to g. This minus multiplies through, and we get 3/16, 1 over w plus w. Now, if the last thing that I did, if you're looking at that going, yeah, no. I took that minus times this, right? So I took this minus and I multiplied through so I could make everything positive to make it easier. You don't have to do that. You can leave those minuses in. It will still work. Okay. So now it is time to pay the piper. And what kind of piper do we have to pay? Well, the piper that we need to pay is that we don't know what these values are. So we have two choices. One, we can resubstitute back w to theta to u to x and use the original limits. Okay, you're welcome to do that. I don't want to do that. 2. We can convert the original limits to W. And that's the way I want to do it. I'm going to go ahead and bring the units forward. Now, it really depends on the situation. Sometimes you might choose to actually go back to the original x. I'm not going to worry about that. Now, if you had all the way along converted every time you had a new set of limits, you'd be done. You wouldn't have to do that. So this is another example of the way that in math, you either have to do the hard work up front or you have to do the hard work at the end. And you can really choose when you do it. There's a lot about it that you can choose. Okay. Woo. So what are the limits? Okay. So this is page, I believe, 6 at this point. So what were the limits? We went from x to u to theta to w, right? Those were our substitutions. So in the world of x, we went from 0 to 3 radical 3 all over 2. Okay? So if I want to convert it to u is equal to, the substitution was 2x. So our new limits are going to be 2 times 0, which is still 0, and 2 times 3 radical 3 over 2. And the 2's just cancel, and we get 3 radical 3. Okay? And this is what we would have had to do while we were doing the problem. Okay, so that's x to u. Next up, we want to do u to theta. So in u land, 0 to 3 radical 3, if I want to convert to theta, theta was equal to what? Well, this one's a little bit harder because we had that u was set at 3 tangent theta, right? And so u over 3 is tangent theta. So arc tan, or tangent to the negative first power of u over 3 equals theta. Okay? Okay, so if we want to convert it to theta land, down at the bottom, we're going to have to take arctan of 0 over 3. And up here, we're going to have to take arctan of 3 radical 3 over 3. Okay? So for theta, and this I'm just going to have to tell you, the arctangent of 0 over 3, which is the arctangent of 0, is actually equal to 0. The arctangent of 3 radical 3 over 3, this is going to be arctan of radical 3, and that's actually pi over 3. It's 60 degrees. Okay, we're nearly there. Okay, we're going to go way over. This is page 7. So we want to now go from theta finally to w. And in theta, I just told you I had 0 to pi over 3. And in our conversion to w was the cosine of whatever theta was. So we're going to have cosine of 0 and cosine of pi over 3. cosine of 0. So what is the cosine at 0? It's the x value. It's 1. And what's the cosine of pi over 3? That's 60 degrees. That's the tall one. I always remember 30 degrees is the short angle and pi over 3, 60 degrees is the tall angle. So cosine is small at that value, and that's 1/2. So cosine of 0 is 1. Cosine of pi over 3 is 1/2. We are nearly there. So we're going from the original, way back in the beginning, from 0 to 3 radical 3 over 2, all the way to from 1 to 1/2. So this is in x, and this is finally in w. Okay? So you got to do all the limits, or you can translate back. You go w into theta, into u, and into x. So our new integral is going to be, oh, we're not the, well, the new, yes, sure, I'll write that because I realized I started that. Let me finish that. Where is it? The new integral is from 1 to 1/2. It's 3/16, negative 3/16 of w, oops, you can't see it, there we go, it's negative 2 minus 1 dw, which gives us negative 3/16, and then we got to the opposite of w, the negative 1, minus w from 1 to 1/2, right? And then we said, oh, let's cancel out all the minuses. So we get 3/16 times 1 over w plus w from 1 to 1/2. Okay? We are nearly there. This is very exciting. Are you guys excited? Okay, this is page 8, and I think final. So at this point, the last thing I wrote was that this equals 3/16 times the quantity 1 over w plus w from 1 to 1/2. So this is going to be 3/16 times, now this is going to be 1 over 2 plus 1/2 minus, and then we're going to plug in 1 over 1 plus 1. Right? So I plug in the halves, and then I plug in the ones. This is 3/16. 1 over 2 is 2. So 2 plus 1/2 minus, and this is going to be 1 plus 1, so minus 2. Did you guys see it? Can you taste it? We are almost there. 3/16. 2 plus 1/2 minus 2 is just 1/2. 3/16 times 1/2 is 3/32. And that is the correct answer. We did it, you guys. You're amazing. We did it in under 40 minutes. That's very impressive. Woohoo! You guys are so incredible. So, absolutely, pause this video. Stop this video. Walk away from the video. Go outside. Touch some grass, or look up at the moon, or inhale some fresh air and get some water, maybe a snack. Go pet an animal. Tell someone you love them, and then come on back and look at the notes and see if you can figure out what we did. It's a lot of steps. There were 4 substitutions. We went from, or I guess technically 3 substitutions. We went from x to u to theta to w. So there are 3 substitutions and 4 variables, and that's a lot, but you made it. And I hope the takeaway is you won't always be able to see that it's going well, but you should just keep going and see it through. A lot of times it will actually get worse before it gets better. But hopefully, eventually, you get to something where you can actually do the math. And it turns out this math wasn't that hard. So we did it, you guys. Okay. We just popped up over 40 minutes. So I'm going to say goodbye, good night. Have an amazing day / night / afternoon. Know that I'm incredibly proud of you. And Square Bear is very excited and very proud of you too, because we ate all those square roots. So you did a great job. And I will see you in the next video. Woohoo! Math on.